What's up? This is your video for your notes for geological dating. This is going to be part one, relative dating. And let's get started. Grab a pencil and some paper. That's all you need. So when we're talking about geologic dating, we're basically talking about trying to put events in order. What happened first? What happened last? So when you look at this image, you might come up with a conclusion as to what happened. First, we had a thunderstorm. And then obviously after that, a child ran through the mud puddle. We then had hailstones that fell during the thunderstorm and the mud puddle dried. The heat from the sun caused cracks to form, and that's the story behind the dried mud puddle. Now, you might be asking yourself, well, how do I know the hailstones didn't fall before the child ran through the mud puddle? If you look carefully at the image, you'll see that there's actually a hailstone inside of the child's footprint. So that's a clue that the hailstone had to have came after the child ran through the mud puddle. Again, we're just trying to put events in order. So in your notes, I want you to write down relative dating. And all we really use relative dating for is to estimate age. So you're figuring out an order of things that happened. All right, let's keep going. Hopefully you wrote down relative dating in your notes, used to estimate age, and it's used to figure out what order things happen in. Okay, an index fossil is a very specific type of fossil. An index fossil actually helps us determine the age of a rock layer. Now, it has to be an organism that lived for a short amount of time, and as we see on the notes, it has to be found throughout the entire layer. These organisms were distributed widely, not just in a small area, but in a wide area. And I want to go to the next slide so I can explain this image. So make sure you wrote down index fossil, lived for a short time, found throughout entire area. And so when we look at this image, we're trying to figure out which one of these four fossils could be used as an index fossil. The shark tooth and the brachiopod, definitely not good index fossils because we're finding those in multiple rows, which means that the shark lived for a very long time. We're looking for an organism that only lived for a short amount of time, so it should only be found in one row. I think you found it, the trilobite. The trilobite is only found in row 2, but it's found in every single outcrop. So if we can figure out how old the trilobite is, that will give us a big clue how old this rock layer is. So index fossils can be very useful. All right, let's move on. Original horizontality. All this is trying to say is that layers are deposited flat. Go ahead and write that down. Original horizontality, layers are deposited flat. They're not slanted or tilted. As we can see in the image, the man standing down at the bottom, to his left, we have younger layers of rock, which are nice and flat. On the right, these have been bent, these have been curved or slanted. So these are older. Again, just write down original horizontality, layers deposited flat. All right, and original horizontality actually leads into the next thing I want to talk about, superposition. Superposition is just trying to tell you that the layers on the top are younger than the layers on the bottom. Go ahead and write that down. Superposition, youngest layers on the top, oldest layers on the bottom. This tells us that the deeper this man digs, the older the rock layer will become. You can get a great sense of superposition if you're able to visit the Grand Canyon. As we can see looking in the distance, all of these layers of rock, theoretically, the deeper we go, the older the rocks get. All right, now let's talk about cross-cutting. All right, when we talk about cross-cutting, I want you to think back to the San Andreas Fault. Yeah, that big fault line over in California. Now, that fault line got there after California was already there, right? You had to have had a rock to break it. So faults are always younger than the rocks that they cut. Go ahead and write that down. And you can think about a fault when you think about a crack in a road. Obviously, the road had to be there first before we can have the crack. So the fault came after the road layer. All right, now let's talk about igneous intrusions. Igneous intrusions are basically where magma has boiled up from Earth's interior and it's trying to get to the surface and it moves through rock layers. Now, those rock layers had to already have been there before that magma could move through them. So the intrusion is always younger than the rock that it breaks through. Let's see if you can find the intrusions on this image. I'll give you a few seconds. All right, you should see two intrusions. We have one over here coming straight up, And then we have another over here to the right. Comes up about halfway and then flattens out. That tells us that when this intrusion occurred, this was the surface. And this is where the lava flattened out on top of the surface. This gray intrusion is younger because it breaks all the way through and it keeps going to the new surface. All right, now let's talk about inclusions. Now, I know we just talked about intrusions. Now I'm mentioning inclusions. Don't let those words trip you up. Intrusions is the magma pushing through. Inclusions is like when something's included for free. So we see pieces of older rock have been trapped in younger rock. Go ahead and write that down. Looking at the top right, we see rock B and rock A. Rock A is the orange rock. Rock B is this brownish rock. So rock A is trapped inside of rock B. That means rock A is older. Rock B is younger. Whatever's trapped inside is the older rock. Here's another example. On the bottom left here, granite is older because granite is trapped inside of the sandstone. However, on the right here, for example B, we see that the sandstone is being trapped by the granite, which means that the sandstone was older than the granite. So A and B are two different images. Don't let those trip you up. Just remember, inclusions, just like a Happy Meal includes a toy inside, inclusions include pieces of older rock trapped inside younger rock. Unconformities, these are caused by weathering and erosion, and basically, it's layers of rock that have been washed away, carried away, and now we don't know where they are. That's a gap in the rock record. So if we look at this image, we can see this squiggly line marks where the erosion and weathering took place. All of the layers that were above that line have now been washed away. We don't know how many layers used to be there. Needless to say, it's a gap in the rock record and it's gone now. All we have to read is this gravel and clay that have been deposited on top of the unconformity. All right, guys, I want you to practice. Look at this image. Try to think what happened here. I'll give you a few moments. Are you ready to find out what happened? Here we go. It all started on the top left with some nice horizontal layering. There used to be a lake bed, and then it dried up. So now we have these flat layers that are just kind of getting weathered. Eventually, we see that there was some inclusion starting to form in here, and now an intrusion has taken place. Magma has pushed its way through the surface. Over here, we're noticing, oh no, some erosion has taken place. We've lost some of the rock record. An unconformity has formed, and the rock layers have shifted to the side. So now we have the rock layers being tilted, so they're no longer horizontal. After that unconformity, new horizontal layers are placed and a new lake forms, and then the lake dries up and we have more erosion. Again, it's kind of hard to see that from looking at this one image, but basically you're just looking at relative dating. What happened in order? What came first? What came last? All right. Thank you guys for watching my video. I hope you like and subscribe. I'll see you in the next one.